Good. Well, let's prove some more useful things about spectra. The homotypic groups, the homotypic classes of maps from one space to another space do not form a group in any meaningful sense. Not so for spectra. In other words, the Hom functor is the homotypic category of spectra, which is the same as the stable homotypic category, is enhanced in abelian groups. Okay, now the problem with this, we don't have a model structure yet. So we will prove this for CW spectra. For CW spectra, we have the notion of homotopy, which, as I mentioned last week or the week before, corresponds to the categorical notion of homotopy. If the cylinder objects are cylinder objects. Now we cannot expect to have any sort of group structure on the nose, which is why we need to pass to the homotypic category, and so we have to deal with cylinder objects, as otherwise we don't know how to describe the maps in the homotypic category. Well, there are basically several ways to introduce a natural group structure on the homotypic classes of maps. And the results are the same. We know that for spaces or let's say for base spaces. Let's say we have two base spaces. Then we have a group structure on the maps from sigma x to y. Another group structure from on the maps from y to from x to omega y, and those are the same. Which is why I write isomorphic here. If we take maps from the double suspension or into the double loop space, or from a suspension into a loop space, then we the group structure from the previous formula is abelian. So no surprises there. And for spectra, every spectrum is up to homotype equivalence. Every spectrum is the suspension of another spectrum, and every spectrum is the loop space, the loop spectrum of another spectrum. We just saw this last time. So for spectra, the suspension and loop functor are equivalences. So there are two ways to introduce. So suppose we have x, y. There are two ways to introduce the group structure. Well, first we we take a spectrum X, and suppose we have two maps from sigma X to Y. Well, since we want to have enough maps to get everything in the homotopy category, we need to allow those F and G to be partial. Partial maps, by the way, does anyone remember what those are? Что такое частичное отображение? Кто-нибудь помнит? Что-то такое. Yes, a partial map, let's remember, is just a map, but only defined on a cofinal subspectrum. The inclusion of a cofinal subspectrum induces an isomorphism of homotopy groups. So, from the viewpoint of the stable model structure, we don't lose anything if we allow maps to be only defined on a cofinal subspectrum. So, suppose we have two partial maps from sigma X to Y. This gives us a partial map from by taking the wedge of those, we get a partial map from sigma X to sigma Y, and then we compose with the usual map from the suspension to the wedge of the suspension in itself, and those all this data gives me another partial map from sigma X to Y, and well, basically this is all there is. Well, similarly, if I have Fg X and Y, again partial maps. I use the same procedure as for spaces to get a group structure on maps from X to omega Y, and this gives me actually a group structure on everything, because both sigma and omega are equivalences. Well, at least in the homotopy category. And when we take maps from sigma x to omega y, we get the same operation whether we use sigma or omega, and this follows from the same result for spaces. Okay. So we have two ways to equip the set of the homotypic classes of maps by to get a group structure on the homotypic classes of maps, and those two ways give the same result. And this same result is abelian because every spectrum is the double suspension of some other spectrum. So the natural question is, so we have the homotypic category of spectra, and all spaces of morphisms are abelian groups. Is the category of spectra abelian? And the answer is no. It's not abelian, but it's triangulated. Let's see what the distinguished triangles are. The distinguished triangles are the fibration and co-fibration sequences. And there are, let's start with the co-fibration sequences. There are two ways to define those, and one is more explicit, and the other one is cleaner. So let's give two definitions. Let's remember what the co-fibration sequence, what the words co-fibration sequence mean for spaces. Does everyone remember the cofibration sequence for spaces? Okay. Now, suppose I have a CW spectrum and a CW subspectrum. Can I do the same thing? And if no, then what is it exactly that prevents me from doing the same thing? So, remember for spaces. This works for CW complexes. Does it work for spectra? And if it doesn't work, then why doesn't it? Well, the question is how exactly we attach the cone over A. Are there any problems? Let's think. Well, the inclusion map. The only source of potential problems is this inclusion map. It's only partial. So we may have some suspension of a cell which is an A, but the cell itself may not be an A. But this Well, I don't think this changes anything. If we want to collapse the CA, then there are problems. We may only collapse subspectra which are closed, meaning if some suspension of a cell is inside the subspectrum, then the cell itself in the subspectrum. Otherwise, collapsing doesn't work. But here we only attach. We don't collapse anything. So I think the answer is if we define the sequence as for spaces, the procedure works as exactly in the same way it does work for spaces. So. Let me think a little. So we in this okay. So in this particular example, we have maps which are shown here, but we also have this map. And the question is, do I want to include it as part of the definition, in the same way as for distinguished triangles we have the connecting homomorphism as well. If we have a distinguished triangle in a triangulated category, we need to specify the map from okay. So yes, let me consider this as part of the data, because it's well, similar because it's better this way. So we have this identity, but for spectra it's it's not for free, or is it? No, I think for spectra it's to prove this identity, we do need to collapse what? We need to collapse Cx. Yes, but Cx is a closed subspectrum of this thing. So we don't need to worry about collapsing. Causing problems. Okay, so we a cofibration sequence is a sequence of maps in the homotype of maps in the homotypic category of spectra, such that. The result is the result. Okay, the inclusion of a CW subspectrum gives me maps from a subspectrum to the big spectrum, and then to this, and then to this, which is isomorphic to this. Okay, so if I get something in the homotypic category which is isomorphic to what one gets from the inclusion of a subspectrum, I call the result a fibration sequence. Sorry, a cofibration sequence. Does this make sense? Does the definition make sense?
So from this inclusion, you just collapse every cone?
Well, one needs to be careful. If we want to collapse CA, we need to assume that A is closed. If we want to collapse CX, there aren't any problems. It's automatically closed. So we have an isomorphism between this and sigma x, which is the same as x shifted by 1 to the left. Now I want to prove I want to give another definition. So this is first definition. And the second definition. Please pay attention to the indices, and if they look messed up, please let me know. Okay, second definition. Suppose we have a sequence in the homotypic category as shown, as a cofibration sequence if for every W which we x1 W ZW YW XW is exact. Okay. Now let's prove that. By the way, did I mess something up? Let's prove that those two definitions are equivalent. Well, suppose we have the inclusion of a CW subspectrum. I need to show that the sequence and okay, W is just a spectrum. CW well. Okay, so let me first show that the exactness in this term, and then I will I will just say that the exactness. The exactness in the remaining term follows by shifting the sequence for spaces. Okay, so we want to show that the sequence W X W A W is exact. And by the way, as everyone probably realized, exact the word exact makes sense because we've just seen that those are abelian groups. So the word exact, just as usual, means the image is the same as the kernel. Well, everything is clear except the inclusion of the kernel in the image. In other words, suppose I have a map from X to W, which is trivial when restricted to A. I want to extend this map to X union CA. Well, it works exactly the same as for spaces, but we need to pay attention to the fact that the maps need not be everywhere defined. So suppose I have suppose I have a map which is null homotopic, meaning homotopic to homotopy to a constant map, where by a constant map we mean a map which factorizes through the inclusion of the base point. Well, so what do we do? Well, we well, again, we have we have some final subspectrum on which F is defined, and let's assume that this X prime also contains by the way, we don't need to assume this. If we have a cofinal subspectrum and some subspectrum, then we don't need to assume anything. And X prime contains a cofinal subspectrum of A. Okay. Let's call this subspectrum A prime. We have a no, we also need to choose a cofinal. Okay, let me put it this way. There is a cofinal subspectrum Ca double prime, which is cofinal in Ca, which contains Ca prime, and on which on which the null homotopy is defined. The problem with those partial maps is that the homotopies are also partial. So the null homotopy may not be defined on A prime. It's defined on some cofinal subspectrum of A cross, A wedge the interval, and so technically we take A prime, which is cofinal. We would let's recall the definition of a homotopy. In the definition of a homotopy, we use X wedge 0, 1 plus okay, so so a null homotopy let me put it this way. A null homotopy a null homotopy this is not good. A null homotopy for for a genuine map from A prime to W gives me a map on a cofinal subspectrum of CA, which I denote a CA double prime to W. So we basically, after all this long discussion, we basically use the same idea we used for spaces. Okay, so we proved that the sequence is exact in in the middle. Well, not in the middle, in this term. Well, now I want to prove that the sequence is exact in this term, but this follows from what we've just seen. Why? So we get the exactness. We get exactness in one term and observe that if we have a CW subspectrum, then X union CA union CX let me just write here. This is sigma A, and this is something which is in fact sigma X. Let me just write sigma X. If we have this, then the shifted sequence is also a cofibration sequence. According to the first definition. And the sequence of the HOMs into W is exact here. And this gives us exactness of the original sequence in this term. Well, basically, there's a small problem. The letter X denotes two different things. Here we have an X, and here we have another X, and those are two different X's. I do apologize. It's very bad. Well, anyhow, does this make sense? Any sense? Any kind of sense? Okay. Well, now I want to prove. I want to prove the. So this shows that if something is a cofibration sequence according to the first definition, it's also a cofibration sequence according to the second one. Now I want to show the converse. So, but this is after this is all we'll talk about today. There's also the vibration sequences, which we'll talk about next time. Well, so how to prove that if we have a cofibration sequence with respect to which is a cofibration sequence according to the second definition, how do we construct a CW inclusion? Well, it's very simple. We basically may assume that X X to Y is a CW inclusion. So we have X, Y, X union CY. Very well. This is isomorphic to X to Y. And now we have a Z. Okay, now I want to compare this abstract Z with X union CY. How do I do this? Is there a map from Z to CY to X union CY, or the other way around? Anyone? Okay, firstly, the composite map X to Y to Z is null homotopic. Why? Well, because I know that the sequence of the Homs, this thing is null homotopic. Why? Because the sequence of the Homs is exact. For example, I can apply this thing to the identity of I take the sequence, I take the Homs into Z. Okay, I get something exact. In particular, the identity of Z will go to 0. Well, what does this mean? This precisely means that the composite is null homotopic. Because what is this composite? This is the result of applying Hom to Z to the identity of Z. Does this make sense? So here we apply. Okay, so this composite is null homotopic, so using the same sort of strategy we used here, namely we have the composite which is null homotopic, so I get a map from X union CA to blah blah blah. I get this, so I get a map by the same argument as before. And now what do I do? Well, one thing I could do is take Homs into any W. And I get a long exact sequence from the first row and another one from the second row. And for long exact sequences of abelian groups, I can use the 5 lemma. And so by 5 lemma, так имеет ли смысл происходящее или уже все, пора закругляться? Maybe. Oh yes, sorry. Yes, absolutely. Yes, a very good question. X is a subcomplex, so we attach a cone over the subcomplex. So it's good to know that someone's paying attention still. Anyway, but we still want to use the 5 lemma. Okay, I'll erase this part. We're almost finished. by the 5 lemma, the map by the 5 lemma, the map which we want to show is an isomorphism in the homotypic category, induces an isomorphism of the abelian groups, hom into W. How do we finish the argument? So we have this map of spectra, and we want to show that this map is an equivalence. In other words, an isomorphism in the homotypic category. We take an arbitrary W and consider the map of the homs into W induced by this map. And we know that by the 5 lemma it's an isomorphism. Why? Exactly. So by Yoneda, this map is an equivalence which is the same as an isomorphism in the homotypic category. Okay, very well. So what did we do? We proved that if we have something which is a Gof vibration sequence according to the second definition, it's also isomorph. Well, at least it's isomorphic to a Gof vibration sequence with respect to the first definition, if we manage to prove that this square commutes. Okay, so question for everyone to think about. Why does so we've we know that these two squares commute. Why does this one commute? Okay, so this is something to think about, and we'll discuss it next week. Are there any questions? Well, then this is it for today. And by the way,